In order to reach the stars, we will need spaceship drives of titanic output, even those powered by the stars themselves. So over the years, we've reviewed a lot of spaceship designs in our overall discussions of humanity's future and of space colonization in general, some in depth and some only in passing, and some in episodes that were made so long ago that they're buried in search engine results. And since our Megastructural Compendium episode from last summer was well received, I thought we might follow that up today with a list of all the various advanced spacecraft propulsion methods that are either on the drawing board, represent popular theories, or even just things that are regularly and seriously discussed in science fiction. Each will have its own alphabetical entry, and those on YouTube should see a chapterized version available, and we'll have a time index of topics in the description on all of our platforms. If you review those, you'll note that some aren't very advanced drives at all, or even propulsion methods, as I felt that certain critical topics like the rocket equation or what specific impulse is should be in the episode, especially as while you can listen to this episode all the way through, it is not necessarily intended to be absorbed in that way like most of our episodes incline towards. It's also going to be a long one, so a drink and a snack is advised, and my wife Sarah will be calling out the titles and references between episodes to help distinguish the breakup of the individual entries. Also, at the end of every entry, there would be a list of other entries related to the topic or mentioned in the entry, and we will sometimes reference relevant episodes, and for viewers, the cover art of that episode will appear as the thumbnail on screen to help you find that episode, as YouTube limits us to 5 in-video links and also 100 chapters, which we discovered with the previous Compendium episode, and is part of the reason why some of our topics are merged. One of the others being that some are very similar, especially without getting into technical details that most casual watchers wouldn't follow. Indeed, being a physicist rather than an aerospace engineer, there are a few that I'm not sure I do either, and there is a reason why rocket scientist is synonymous with being very smart. I would also like to note that virtually all of these ideas are someone's brainchild, whether it was a scientist or sci-fi writer or both, and for brevity's sake, we're not delving into the full backgrounds and bios of the devices and their designers, especially when the device is named for them, though that means folks like Mark Millis, who proposed or expand on tons of hypothetical drives, like the bias drive, diametric drive, disjunction drive, pitch drive, and more, are not getting anything like the credit they deserve. I can only say that for as long as this episode is, much is being left out, and there is mind-bending science, fascinating development backgrounds, and amazing science fiction out there for those who choose to go beyond these short entries and explore these topics more. If you are looking for good places to continue finding out more on these drives, I definitely recommend the National Space Society, Tau Zero Foundation, Atomic Rockets, Centauri Dreams, Orion's Arm, and of course NASA's EagleWorks Lab. With all that said, and without further ado, let's get started.
Alcubierre Drive.
The Alcubierre warp drive is a well-known example of a type of warp drive that uses hypothetical negative matter or negative energy to warp space-time in front of a ship to contract, and behind a ship to expand. Because the ship itself is not accelerating, this not only allows high speeds, but bypasses normal limits on the speed of light in the same way dark energy and Hubble expansion do. Because of it requiring exotic matter not currently known to exist in nature and permitting faster than light or FTL travel, this technology is an example of Clarketech, technology so advanced they are indistinguishable from magic and to which we have no clear scientific pathway to produce, and is very similar to an induction ring drive as it is creating a bubble of warped space around the ship. See our episode on warp drives for more on the Alcubierre Drive.
See also Bias Drive, Clarketech, Diametric Drive, Disjunction Drive, Pitch Drive, Warp Drive. Antimatter Ablated Light Sail.
As antimatter is thought to be hard to produce and store, various rationing ways to use it in tandem with other materials have been contemplated, and this includes the antimatter ablated light sail. This technique involves a small supply of anti-hydrogen, maybe just a few grams for smaller ships. This uses anti-hydrogen slowly released toward a forward plate or dish akin to the Medusa Drive, made of uranium-238, which might be as small as a few meters, allowing a relatively small ship. The antimatter reaction with the U-238 should produce neutrons and other secondary products which would leave the sail at very high speeds, and produce a power rate of a couple megawatts per kilogram of sail. Such ships may be able to gather the necessary antimatter from natural sources such as gas giants.
See also Antimatter Rocket, Antimatter Catalyzed Fusion, Medusa Drive. Antimatter Catalyzed Fusion.
We have been pursuing artificial fusion with varying but improving degrees of success for decades, but one of the most promising methods is antimatter catalyzed fusion. Using small amounts of antimatter, we can catalyze far larger bursts of fusion, releasing far more energy than the bit of antimatter held, and is believed to be a fairly simple process. This could either run a fusion reactor to power ion drives, or simply be used for micro-fusion bombs right behind the ship as an effective fusion rocket. Unfortunately, it requires a small supply of antimatter, which is barely existent naturally and hard to make and store. Should we find a way to make and store antimatter, but not in sufficient quantities for a full antimatter rocket, antimatter catalyzed fusion could allow a fusion torch drive behind a ship, allowing it to travel at very high speeds, possibly in excess of 10% of light speed.
See also Antimatter Rocket, Antimatter Ablated Light Sail, Fusion Torch Drive, Nuclear Pulse Drive, Orion Drive. Antimatter Rocket.
Antimatter is matter with the opposite characteristics of normal matter, and when particles of antimatter such as the antiproton or antielectron, better known as a positron, come into contact with a proton or electron respectively, they typically turn into a pair of photons containing the total mass energy of those particles. By itself, this is not explosive and occurs often enough in nature, as many particles emit positrons during decay, including inside your own body, and rapidly find an electron to mutually annihilate with. In large quantities, antimatter makes a nuclear bomb look weak, as a single kilogram of antimatter would combine with a kilogram of mundane matter to release the equivalent of a 43 megaton hydrogen bomb, equal to the Tsar Bomba, which was the largest thermonuclear device ever tested, which also weighed 27,000 kilograms, not just one. Antimatter has the second advantage that doesn't require any other hardware to do its job, other than presumably magnetic containment. The difficulty of making it and storing it are the two main limitations, and the basic theory and technique for producing antimatter are discussed in our episode Antimatter Factories. Assuming you can make and store it, antimatter, along with an equal amount of mundane matter, can be easily magnetically sprayed into your equivalent of a rocket nozzle and form a photon rocket with an exhaust velocity of light speed. An antimatter rocket such as the theoretical Valkyrie spacecraft was expected to be able to reach 92% of light speed, at which speed the crew of the ship would be experiencing less than 10 hours for every day here on Earth, or 40 years for every century. For this reason, antimatter is generally considered the most powerful rocket fuel available under known science. However, due to its incredible rarity in nature and difficulty to produce and store, more frugal uses of antimatter are often considered, such as the antimatter ablated light sail and antimatter catalyzed fusion.
See also Antimatter Ablated Light Sail, Antimatter Catalyzed Fusion, Photon Rocket. Arcjet Rocket.
The Arcjet Rocket or Thruster is an electric spacecraft propulsion method commonly used in small spacecraft, as it is simple and small. An arcjet that uses a pair of electrodes to generate an electric arc, the same as a conventional arc welder, that in turn vaporizes the propellant and pushes it back. The arc and propellant, now plasma, then continue backward through the thruster, gaining speed from the anode and cathode. This is an example of a low-thrust, high-efficiency rocket, as very little thrust is produced at any given moment, but the exhaust velocity is very high. Ammonia, a popular Arcjet rocket propellant, typically has an exhaust velocity of 9,000 meters per second, more than double that of a typical chemical rocket. The Arcjet is generally more efficient than its cousin, the Resistojet, but both suffer from some durability and longevity issues, particularly of its electrode, which electrodeless designs such as a pulsed inductive thrusters seek to circumvent.
See also Pulsed Inductive Thruster, Resistojet. Bias Drive.
A bias drive is an example of a Clarketech engine that works not by warping space or time, but by locally altering physical constants of the universe, in this case the gravitational constant, in front and behind the ship, letting it essentially fall to its destination. Beyond having no method to alter physical constants at this time, it is likely that a bias drive would produce a singularity in the center of the ship. If functional, however, such a ship would not need to expend any fuel to move from point A to B, and a bias drive would appear to allow perpetual motion machines for producing electricity and power, though it is entirely possible that techniques for changing physical constants might still conserve quantities such as energy and momentum.
See also Clarketech Pitch Drive. Black Hole Drive.
Black hole drives are a group of hypothetical spacecraft propulsion methods that can range from using naturally occurring ones to accelerate and redirect a spaceship to co-opting one to move an entire star system, as discussed in our episode Fleet of Stars. The most well-known version relies on using micro-black holes in the sub-megaton range to generate Hawking radiation, and Hawking radiation drives are covered in their own section. Other methods include using the Penrose mechanism or similar methods to dump matter into a black hole, presumably a micro-black hole larger than a megaton, and get 20 to 40% of its mass energy released as radiation during the descent. Gaining power from black holes this way is not technically complex, it's simply absorbing high-energy photons coming off it as with any nuclear process, and such black holes may be tethered to spaceships or stations with magnetic fields, which black holes both produce and interact with. Additional uses, which are discussed in our episode Black Hole Ships, would also involve using them as the power plants of ships running photon rockets, using them to power giant laser pushing beams, such as we contemplate for laser sail and pushing relay stations, or even using them in pairs for accelerating ships around them in a loop to achieve high speeds.
See also Hawking Radiation Drive, Laser Sail, Matter Beaming, Photon Rocket. Bussard Ramjet.
The core concept of the Bussard Ramjet is that most of space is full of ionized gas particles, most of which are hydrogen, a ready source of fusion fuel, and if you can grab these magnetically and suck them down into your ship, you can use them as a fuel. The ramjet part comes from parallels to how an air-breathing ramjet works, sucking air in and superheating it, then shooting out the back. But here the power source for heating that gas up is the gas itself by fusion, and that fusion is ignited by sucking in interstellar gas at relativistic speeds and jamming them tightly down the throat of the ship to ram into other gas particles at high speeds, temperatures, and pressures. This seemed like a possible way to give ships an infinite power supply, simply grabbing out of space as they flew by, like a ship sailing on a sea of diesel fuel. Indeed, it was contemplated for a while as a way to keep accelerating indefinitely, something we see in the sci-fi classic novel Tau Zero, or with other drives like the Gravitic Dipole or laser sail, but the math turned out not to work. Indeed, some argue the method would actually require more energy than the reaction released and result in the ship slowing, which ironically makes this drive handy for decelerating for free, which would make it function very well with a laser sail and relay system on the front end of the journey to push the ship up to speed, and the ramjet to slow it on arrival, while also powering other ship functions. Additionally, this technique of sucking in ionized particles magnetically works perfectly fine if you have otherwise functional fusion reactors and are not planning to move in excess of what the ship's normal exhaust velocity is, and thus works just fine for giant ships with conventional fusion reactors who only plan to move a few % of light speed. This might include freighters, deep space miners, monitors or patrols, or giant beaming stations, be it laser, energy, or matter beams, needing to do station keeping and to resupply their fuel. It also works just fine if you have a refuelable black hole in the throat of your ship, into which you're stuffing in matter you sucked in, though only to whatever speed your effective exhaust velocity of that system would be, since otherwise you're sucking in matter that you have to absorb the momentum of to use for power and propellant, which would exceed what you were getting out of it. This makes it handy for big carrier ships wanting to turn directions or launch higher speed vanguards out of, since it can supply power to those too, by laser or energy beaming. So the Bussard Ramjet wouldn't work as planned, but they do have some variations and alternative applications worthy of note.
See also Black Hole Ships, Gravity Dipole Drive, Laser Sail, Matter Beaming. Caplan Thruster.
A Caplan Thruster is a method for moving stars proposed by Matthew Caplan in 2019 for using statites to concentrate solar energy and erupt solar wind in a beam out from a star, which would then pass through an enormous Bussard Ramjet assembly and jets of oxygen-14 to push a star at a far faster rate than a traditional Shkadov Thruster would allow. See our episode Fleet of Stars for more discussion of potential methods of moving stars.
See also Bussard Ramjet, Helios Drive, Nova Drive, Quasar Drive, Shkadov Thruster. Chemical rockets.
Chemical rockets is the ballpark term for any rocket running on chemical interactions, but generally refers to those running on combustion and producing the classic high-intensity rocket flames seen in countless rocket launches. In such cases, the fuel is typically burned with an oxidizer to emit a propellant that, because of its high temperature, also has a high exhaust velocity, allowing it to exit the rocket nozzle with a high momentum while pushing the ship in the opposite direction with that same momentum. Chemical rockets typically have far higher exhaust velocities and specific impulse than other alternatives such as compressed gas, as is used in CO2 cartridge guns, pumped water rocket toys, or other alternatives such as the elasticity that traditional catapults or bows use for firing a projectile. Because combustion occurs very quickly, it permits a spacecraft to have enough thrust to escape from a planetary gravity well, whereas more efficient ion drives could never get off the ground or clear an atmosphere, even though they will ultimately push a ship to a far higher speed. However, as a result, chemical rockets are most efficient at high temperatures, and so we run their combustion as hot as the rocket body and nozzle can withstand. The most efficient known chemical rocket fuel is molecular hydrogen burned with oxygen, though it is more difficult to use compared to its more commonly used counterpart rocket fuel, which is essentially kerosene. Many other fuels have advantages in certain conditions or environments, or are easier or safer to work with, or easier to obtain, which becomes critical in wanting to source your fuel from your destination for a return trip, in situ production of fuel from whatever is available on the Moon or Mars or elsewhere.
See also ion drive, propellant, oxidizer, rocket equation. Clarketech.
Clarketech is not a propulsion system itself, but a category applying to many possible propulsion methods suggested in hypothetical science or science fiction. The name is derived from Arthur C. Clarke's famous quote that any sufficiently advanced technology is indistinguishable from magic, and is the name for various technologies that folks have suggested that would not seem possible under currently known physics, and can include negative matter or other exotic matter types, as well as faster-than-light systems and perpetual motion machines. It would also include propulsion technologies that operated by altering physical constants, such as the speed of light or force of gravity, or the electromagnetic or strong and weak nuclear forces, or bending spacetime in strange fashions, like creating a circle with only 359 degrees inside, or portals to other dimensions with different properties. See our episode Clarketech for more discussion of these neo-magical technologies.
See also Alcubierre Drive, Bias Drive, Diametric Drive, FTL Drive, Inertia Reduction Drive, Krasnikov Tube, Pitch Drive, Negative Matter Propulsion, Warp Drive, Wormhole Drive. Diametric Drive.
The Diametric Drive is a hypothetical Clarketech reactionless drive typically envisioned as running on negative mass, but may work on any field or force which can be used to create an effective pressure difference on the ship to push it along, much as an airfoil in the atmosphere works. A property of negative mass particles is that they are believed to gravitationally repel both positive and negative mass, unlike positive mass, which is believed to pull on both positive and negative mass. Therefore, two positive mass particles pull toward each other, two negative mass particles repel each other, and a positive and negative mass particle will actually shove the positive mass away from the negative mass, while pulling the negative mass toward the positive mass, resulting in a positive mass particle being chased by the negative one. This technology is akin and equivalent to a gravitational dipole drive, where gravity is the force or field being used for propulsion. Diametric drives are a subcategory of pitch drives, and again may use negative energy to achieve this push or other effects, and is very similar to a tractor beam, which might also be used for spaceship propulsion.
See also Bias Drive, Clarketech, Gravitational Dipole Drive, Pitch Drive, Negative Matter Propulsion, Reactionless Drive. Disjunction Drive.
The concept behind the disjunction drive is that a field might be disjoined from the object that created it. Conceptually, we might imagine a ship built near a large gravity well, which was then disjoined from the mass creating it, and potentially reattached to the front of the ship so it constantly fell forward. We might also disjoin something's inertial mass while leaving its gravitic mass in place, or disjoin an electrostatic or magnetic field from their generator. This could also be a disjunction from a Higgs boson field. Needless to say, such technology would be Clarketech.
See also Bias Drive, Clarketech, Pitch Drive, Reactionless Drive. The Electric Solar Wind Sail.
Our sun has a surface temperature of thousands of degrees, constantly being stored around by the sun's immense magnetic field, and this results in emission of particles, principally ionized hydrogen, from our sun's surface, moving at hundreds of kilometers per second. It is possible to create a large thin sail that would take these particles and be shoved by them, same as a ship sails the winds here on Earth. But as solar wind is very diffuse, such a sail would need to be very large and potentially impractical, even if made from graphene. Instead though, we might run out conductive cables or wires as thin as a hair, like spokes on a wheel, and kept in a circle by slow rotation of the main body, allowing the equivalent of square kilometers of sail from tiny threads. All these particles are mostly ionized. They can interact with electric and magnetic fields, and in this case electrically, to push the ship along. This method only works inside solar systems, and thus is a good method for accelerating ships to speed or decelerating them once they reach another star to save fuel, if used in tandem with other drive systems. It should be noted that, while all stars have solar wind, the quantity and speed of those particles will vary immensely, as the difference in brightness from the dimmest red dwarfs to the largest supergiants is a factor of over a billion. Stellar remnants may also have more polar particle stream, such as we might expect from pulsars, which interstellar ships might use for both gravitational assist to gain speed and direction, and to ride away on that jet, gaining more speed. So too, technologies such as starlifting, see that episode, which are normally intended for mining a star of its materials, also allows for increasing solar wind and directed streams of denser and higher speed wind, similar to what we might use for matter beaming.
See also magnetic solar wind sail, matter beaming, solar sail. Electrodynamic tethering.
Electrodynamic tethering is an electric propulsion technique available around large magnetic fields, such as many planets like Earth have. By having a satellite with an anode hanging below it attached by an insulated tether, we can run electric current through that system and push away from Earth, shoving on the magnetic field, or deboost by having the tether above instead of below. Due to the size of these magnetic fields, in a physical sense, the tethers must be long to function, typically on order of kilometers of wire, and this technique may be reversed to generate power rather than turn power into thrust. Electrodynamic tethering is often considered an option for regenerating momentum in skyhooks and rotovaders, which lose momentum while helping spaceships move from air to orbit, though vastly reducing their own fuel needs with the boost. See our episode Skyhooks for details. But a skyhook which lost some momentum and altitude by lifting a spaceship to orbit could slowly regenerate that over some hours by gathering sunlight from solar power and using that electricity to run an electrodynamic tether, as skyhooks are already very long tethers themselves. Such technology is also good for station keeping of satellites, space stations, or high orbital variations of a rotovator meant to slingshot a ship into deep space at high speed, and could also be employed near super powerful magnetic fields like those of gas giants, stars, and stellar remnants like white dwarfs, neutron stars, pulsars, and black holes.
See also rocket equation. EM Drive.
The EM Drive is a spacecraft thruster that gained popularity, or notoriety, earlier this century as a potential reactionless drive or perpetual motion machine. As it seemed to exhibit properties violating conservation of momentum, it was catapulted into fame when NASA Eagleworks Lab built and tested one in 2016, and it seemed to exhibit the purported physics-breaking properties, but those were later blamed on measurement errors, and no other experiments have since replicated the desired results. As it appears to be a falsified technology rather than a still hypothetical one, we will not classify it as Clarketech, and we will also not give it further discussion today, other than to say the principle is to supply power to a magnetron into a resonant cavity that is roughly cylindrical but narrows a bit, thus has one side with a slightly smaller diameter than the other, which the microwaves will now bounce between. This is said to produce a larger force on the slightly wider side and a smaller force on the narrower side, for a net force on the object pushing it toward the narrow side, which would be fine from a conservation momentum standpoint, except the claim is that it's producing more thrust than a photon rocket under similar power input would achieve.
See also Clarketech, Quantum Vacuum Thruster, Reactionless Drive. Exhaust velocity.
Exhaust velocity is a critical term to rocketry and spaceship propulsion, and represents the speed at which particles of propellant are being exhausted out of the back of a rocket or ship drive. That velocity, times the mass of the exhausted particle, is its momentum. As conservation momentum requires a ship to gain the same momentum in the opposite direction as the propellant being exhausted, a fuel with twice the exhaust velocity lets a ship travel twice as fast, or the same speed but on far less fuel. Most chemical rocket fuels have an exhaust velocity on an order of a few kilometers or miles per second, and it is typically impractical for a spaceship subject to the rocket equation to go much more than thrice the exhaust speed. Thus, we seek propellants with higher exhaust speeds or drives which circumvent the rocket equation. Fundamentally, all particles moving around as a hot gas do so at a certain average speed based on their temperature and mass. Low-mass particles like hydrogen move much faster at the same temperature as higher-mass particles like carbon dioxide do, and thus are generally preferable propellants, where a simple thermal rocket is involved. Most objects, including rocket nozzles, will melt at temperatures of thousands of degrees, so this is often our limit on exhaust velocity as well, though options like magnetic containment and ion drives circumvent this issue, and can work better with heavier ions. A propellant's exhaust velocity divided by the gravitic acceleration of Earth, 32 feet or 9.8 meters per second, will give the approximate specific impulse of a propellant, or essentially how many seconds a rocket running on it could hover the ship in Earth's gravity.
See also propellant, rocket equation, specific impulse. Field propulsion.
Field propulsion refers to any type of spacecraft whose momentum is exchanged by interaction with external force fields, such as we see in electrodynamic tethering, or any spaceship being launched from an electromagnetic space catapult, such as those discussed in our episode's mass drivers. This also includes more hypothetical or fictional examples, such as most gravitic drives, or various hypothetical external fields, possibly including vacuum energy.
See also electrodynamic tethering, gravitic propulsion. FTL, or faster-than-light drives.
This category includes any method of moving a spacecraft at superluminal speeds, or faster than the speed of light, which can range from tachyons to wormholes to hyperspace and warp drives. As known science generally considers this impossible, it is classified as Clarketech, and methods for doing it usually require exotic matter such as negative matter or imaginary mass, and generally result in time travel and violations of causality. See our FTL series for more discussion of techniques proposed and their strengths and flaws.
See also Alcubierre Warp Drive, Hyperspace Jump Drive, Krasnikov Tube, Warp Drive, Wormhole Drive. Fuel.
Fuel is what keeps a ship speeding up or slowing down, or runs its onboard power plant to keep the crew alive and the equipment running. Most often with modern spacecraft, the main fuel is burned up with an oxidizer, and the byproduct of that combustion is expelled out of the rocket as propellant, pushing the ship along. Not all ships would have conventional fuels, and might rely on nuclear reactors, solar panels, energy beamed in from afar, or exotic materials like antimatter. We also contemplate ships needing no fuel or propellant, a reactionless drive.
See also oxidizer, propellant, reactionless drive, rocket equation, thrust. Fusion torch drive.
While the term torch ship originally referred to a ship that converted matter completely into energy, a fusion torch drive is one that achieves very high speeds by being able to turn fusion fuel, potentially even basic hydrogen, into energy, and the fused remainder into its propellant, heated by that energy. Since fusion occurs at millions of degrees, this is not something that takes place inside a normal chamber, and generally needs magnetic confinement and involves lots of equipment for conversion of released radiation and heat into electricity and then into accelerating propellant, typically by some form of ion drive or plasma thruster. In practice, this would really limit how fast a fusion-powered ship could reach, and how fast it could accelerate up to that speed. This is where the torch drive comes into play, as it is assuming the reaction is taking place at the rear of the ship, and basically acting like a rocket flame rather than a reactor or engine burning gas. A ship able to do this is one that can reach high speed quickly by high thrust, rather than requiring a low thrust from a reaction inside the ship designed not to melt the ship or blow it to bits or erode it all under the intense gamma and neutron radiation. They are all many basic if still theoretical designs. Atomic Rockets has the best collection of them that I know of, and many examples in science fiction, but probably the best known, the Epstein Drive from the Expanse series, is a fusion torch ship design. Fusion torch ships are beloved by space enthusiasts as often being considered the most near-future technology, which definitely makes space travel practical for regular human transport, including interstellar travel and ground-to-space travel. though as we discussed elsewhere, there are lower tech or parallel tech options that should allow interstellar colonization, many of which we'll review today. See our episode Fusion Propulsion for a more in-depth look on the topic.
See also Antimatter Catalyzed Fusion, Ion Drive, Photon Rocket, Torch Drive or Torch Ship. Gravitational Dipole.
A type of negative mass reactionless drive using a dumbbell-shaped ship with a sphere of negative mass on one end and positive mass on the other, able to accelerate due to the suspected properties of negative matter, that it is attracted to positive matter but exerts a push on it. Thus, two particles, one negative mass and one positive, will result in the positive mass fleeing the negative, which is pulled behind it in a perpetual and accelerating chase. This is a parallel concept to the Diametric Drive. A ship using this technique is described by Robert L. Forward. He proposed a simple dumbbell-shaped spacecraft design using a ball of regular positive mass on one side, the front side, and negative mass on the back or stern of the ship. Such a ship in theory can accelerate eternally, though likely would experience drag force on its prow from interstellar gas and radiation, giving it a maximum speed of 99.9 something percent of light speed, making it what is sometimes called a light hugger, a ship that moves at within a tiny fraction of light speed. Such a ship could slow down by flipping over and would accelerate or decelerate based on its ratio of drive mass to payload, and could likely physically anchor itself to any larger object. Such a ship may or may not violate conservation of energy or momentum, though would appear to do so on first glance.
See also Diametric Drive, Negative Mass Propulsion, Reactionless Drive. Gravitic Propulsion.
Gravitic propulsion is a blanket term for any ship drive manipulating artificial gravity or using anti-gravity, directed gravity waves, graviton beams, certain types of tractor beams, or insulating itself from gravity to move. While we typically classify this as Clarketech, and indeed have an episode on the topic, Clarketech Anti-Gravity, it does seem plausible that gravity may be able to be manipulated or produced by means other than raw mass. In theory, a gravity drive might also circumvent normal inertial problems of rapid acceleration, as discussed in Isaac Asimov's fourth Foundation novel, Foundation's Edge, which features a ship using this sort of drive. Normally, rapid acceleration causes damage, as not everything is accelerating simultaneously at the same rate. But when falling into a gravity well, this is not an issue, as the force applies to every particle equally, no matter how strong or fast the acceleration, and ignoring tidal effects. A gravitic engine with this property would permit a safe super-rapid acceleration of people and cargo, which is of inestimable value for short space journeys especially, or those on interstellar ships able to reach ultra-relativistic speeds.
See also Clarketech, Diametric Drive, Field Propulsion, Gravitational Dipole, Inertia Reduction Drive, Negative Mass Propulsion, Reactionless Drive. Hall Effect Thruster.
A type of ion drive, the Hall Effect Thruster was named for Edwin Hall and the Hall Effect, and is recognizable for its rather lovely plasma jet colors that it emits based on the propellant it uses. The Hall effect results in a potential difference perpendicular to a magnetic field, so we can create a cylindrical chamber with a large magnetic solenoid in it, and any ionized particles will accelerate down the axis of that chamber as with a normal ion drive. The magnetic field itself is responsible for ionizing the propellant and shoving it and the electrons out the back to neutralize the ions as they emerge. Hall effect thrusters have been around since before we went to the moon and have seen continual improvement, and come in multiple varieties, as well as achieving exhaust velocities as high as 10 times our best chemical rocket fuels. As is often the case, we have to choose between high thrust or high efficiency, and Hall effect thrusters are very low thrust. The highest power one yet produced is the University of Michigan's, which is a 100 kilowatt thruster massing 230 kilograms and producing just 5.4 newtons of thrust. Force being equal to mass times acceleration, this thruster, without any additional equipment including a power source, would only accelerate at about 0.0022 meters per second, about 4,500 times slower than something falling in Earth's gravity. So by itself, it could not be used to leave Earth. However, one accelerating constantly for an entire day would reach a speed of 190 meters per second, for an entire month, nearly 6 kilometers per second, and if its fuel held for an entire year, 70 kilometers per second.
See also Ion Drive, VASIMR. Hawking Radiation Drive.
A Hawking Radiation Drive is one that utilizes a small black hole to create a photon rocket, as it is believed that black holes evaporate over time, releasing mostly photons, and do so faster as they get lower in mass. A 1 megaton black hole is believed to evaporate at a rate that would release 356 trillion watts of power, and would do so at a slowly rising rate for a lifetime of 1,474 years, while 1 1/10 of that mass, 100 kilotons, would emit 100 times more power and live just 1,000th as long, 1.47 years, and it is usually assumed Hawking radiation drives would use black holes in this mass range of 100 to 1,000 kilotons for operation. Bigger ships would use multiple black holes, not a bigger one, as bigger is lower power for black holes, albeit vastly longer lived and with higher ultimate energy output. Smaller is better, but smaller is harder to make and even harder to refuel, and we have looked at methods of using them as ships, power sources, and weapons in our black hole series, including hypothetical ways of creating them. This does appear possible under known physics, so we do not necessarily classify it as Clarketech, though it is at the hazy edge of that category, especially as it is also difficult to chain the black hole magnetically to the ship and to make the emissions, mostly gamma rays, to leave the ship non-omnidirectionally, as we have no gamma-reflective materials. In their absence, you have to absorb those and re-emit it as heat at a lower frequency that existing materials could then reflect. For Hawking radiation drives, bigger is not better, and again for a bigger ship you just add more black holes. This is not the only way to use black holes as spaceship drives or to move ships.
See also Black Hole Ships, Clarketech, Photon Rocket. Helicon Double Layer Thruster.
A type of plasma thruster, the Helicon Double Layer Thruster, or HDLT for short, excites its propellant to high velocity by using radio waves to break it down into a plasma. It is a similar concept to the better-known VASIMR thruster, and is not subject to building up a charge and needing a neutralizer as an ion drive is by default, nor does it have any moving parts or anything particularly susceptible to erosion for it to function, which makes it a low-maintenance design as long as you have a power supply and remaining propellant.
See also Ion Drive, VASIMR. Helios Drive.
The Helios Drive is a variation of the Shkadov Thruster that incorporates star lifting technology to move stars, and can accelerate a star far faster than the Shkadov Thruster, but achieves a slower maximum velocity because it uses accelerated plasma as the drive, lowering the star's mass in the process. By turning mirrors toward a star instead of reflecting its light in a single direction like the Shkadov Thruster does, we can cause a stream of hot matter to come off that star like a rocket flame. This technique works well for moving dangerously large stars, which might go supernova out of a region of space, as it takes far less time to get the star moving at interstellar speeds, and also reduces the mass of that star, potentially extending its lifetime. A variation of this using Bussard Ramjets to fuse the plasma as it comes off the star to provide more thrust is called a Caplan Thruster. This technology can also be used to boost the surface temperature of a star by statite mirrors over its polar region, such as a red dwarf, to produce a hotter star with a spectrum more like our own, for its equatorial region where the planets and space habitats might be, and is known as star boosting. See our episodes Star Lifting and Fleet of Stars for more discussion.
See also Caplan Thruster, Shkadov Thruster, Statite. Hyperspace Jump Engine or Hyperdrive.
Hyperspace drives are a blanket term for any number of FTL drives that operate by having a spaceship leave this universe to enter into another congruent to our own, that allows for faster travel by either being smaller or having a higher speed of light. As a conceptual example, imagine you want to travel from the western United States to the eastern US, and could leap from the real world onto where you are on a map of Earth the size of a normal piece of paper in an atlas, and just step from where you were to where you want to be, as that map is congruent to the US, and teleport back to the real world as opposed to walking the whole way. Popular sci-fi examples of hyperspace would be Star Wars, Babylon 5, Event Horizon, Warhammer 40,000, and many more. it is more or less interchangeable with the term subspace, superspace, overspace, underspace, or null space, though these are different concepts in mathematics. While many modern cosmological models permit various possible hyperspaces or similar, we have yet to document any, nor any means to transfer between them or survive in such a hyperspace, and for this reason, we will classify this as Clarketech. This topic is discussed in greater detail in our episodes Cheating Reality, The Edge of the Universe, and Folding Space.
See also Clarketech FTL Drive. Inertia Reduction Drive.
Inertia reduction works on the assumption that all objects have an inertia or momentum that must be conserved, and which is based on their speed and mass, specifically their inertial mass, which is seen as different from the mass which generates or interacts with gravity. Inertial mass is how much an object resists being shoved on by something like a rocket attached to it. A ship which massed 100 tons and was able to shift its inertial mass down to 10 tons while in flight should be able to move like an object with the same momentum or kinetic energy but a tenth the mass, thus far faster. It would also do far less damage on a collision with an object, which means it would represent a safer form of space traffic. So too, it could slow down very suddenly, like we often see ships in science fiction do, breaking speed by rapidly restoring its true inertial mass or raising it even higher. Such technology is generally considered Clarketech and may violate conservation of momentum or energy. Inertia reduction technology may also imply access to inertial dampening technology, such as we see in science fiction, for explaining how ships can rapidly jump to high speeds or down from them without painting the ship's interior with the jellified remains of the crew. A feature we might also see with Gravitic Propulsion, which might be considered as a twin technology.
See also Clarketech Field Propulsion, Gravitic Propulsion. Ion Drive.
Ion drives, also known as ion thrusters or ion engines, represent a large category of electric spaceship propulsion, generally any situation where ionized particles, being those with some electric charge, are accelerated in an electric or magnetic field powered by an electric supply. The ion is typically propelled out the back of the ship by the electric or magnetic field at a far higher speed than combustion of a rocket fuel allows. They require an electricity supply, which can be anything from batteries to radioisotope thermal generators or RTGs, to onboard reactors, solar panels, or energy delivered by laser or energy beam. These are typically low-thrust, high-efficiency engines which cannot be used to take off from a planet, but allow for much higher speeds, as they typically could operate for many hours or even weeks in comparison to a chemical rocket, which will usually run for mere minutes at most, but can provide a high enough thrust during that period to escape a planet. For this reason, ion drives are a popular option for situations where power can be provided but haste is not needed, such as an interplanetary voyage or a satellite needing to counter minor orbital perturbations or station keeping. There is no real limit on ion drive exhaust velocity, as fundamentally it is a particle accelerator, and those have achieved velocities as high as 0.99999999988 c, but they are likely to have practical limits on what is most effective.
See also Hall Effect Thruster, VASIMR. Krasnikov Tube.
The Krasnikov Tube is an example of a warp drive for FTL travel, and like other warp drives relies on the existence of exotic matter not experimentally shown to exist in nature, and thus is classified as Clarketech. Under standard special relativity, a ship moving at near light speed will experience far less time on a journey than those outside it will have experienced. A ship moving at 99.5% of light speed will have only 1 day pass for every 10 experienced by those outside, and thus could travel to Epsilon Eridani, a star system 10 light years away, in roughly 10 years, but only experience 1 year on board the ship. In simplified terms, SV Krasnikov argues that in the wake of that ship is a tube that allows a shortcut through time, where someone could make that 10 light-year journey in just 1 year. This allows a fast enough ship to make the journey as normal, but for someone to depart 9 years later in its wake and arrive at the destination when the ship does. This means a ship could depart in the year 2090 to Epsilon Eridani, and a person could leave here in the year 2099, and both arrive at Epsilon Eridani in the year 2100. One should be able to keep a constant stream of ships to a given destination, say one departing the first day of each month, to provide a tube of constant FTL travel between two star systems. However, a two-tube system, one going each way to allow return trips, is generally considered to violate causality.
See also Alcubierre Warp Drive, Clarketech, FTL Drive, Warp Drive. Laser Sail.
A laser sail is very much like a solar sail, bouncing light or other EM radiation off a thin reflective sail to impart momentum and thrust on the ship the sail is connected to, except it allows us 4 options. First, to push on a spaceship by sending a concentrated supply of photons to be absorbed or bounced off the back like a solar sail, only vastly more powerful, and thus allowing a smaller sail to achieve the same thrust. Second, by concentrating a beam, we could also keep it focused on the sail far from its origin source. Third, its origin source need not be a star, but can also be a power plant or relay station, such as a deep space comet converted into a fusion reactor and laser, allowing us to extend range indefinitely. And fourth, it allows us to transfer energy to the ship, be it by solar panels absorbing a laser beam far from the sun, or giant rectennas absorbing microwaves. Depending on circumstances, a ship might take advantage of one or more of these options, even if it had another drive system and power plant. Transmitting energy to a spaceship allows us to run ship operations, but can also allow us to achieve higher thrust by using that energy to superheat a propellant or ionize it and fire it out the back as with an ion drive. Doing this will usually sacrifice a higher final speed in favor of faster acceleration, though such technology can be employed in tandem with a matter beam to potentially refuel the ship's propellant. The propellant can also be used to fire forward and thus slow the ship even though a beam is hitting it from the other side, which is a good way of moving comets, by beaming energy to them from in-system that they use to vaporize ice as propellant to push back against the beam and bring them into a system. So too, if your destination system has a laser beaming array in place, it can slow a ship on arrival without fuel, and we have discussed how to forward deploy these beamers to use them to slow each other on arrival in a new system to help a fleet slow down. Use of laser sails is heavily discussed in the show, particularly on episodes Axis Fleet, Interstellar Laser Highways, and Interstellar Colonization Strategies, where we discuss using relay chains of them between star systems to allow cheap relativistic travel to near light speed.
See also Electric Solar Wind Sail, Magnetic Solar Wind Sail, Matter Beam, Solar Moth, Solar Sail. Magnetic Solar Wind Sail.
A magnetic solar wind sail, also called a wingly or just a mag sail, is very much like an electric solar wind sail, using the stream of ionized matter emitted from the sun to drive it to speed, but can take advantage of superconductors, especially high-temperature superconductors, to speed or slow or maneuver inside a star system by using the solar wind. It should also be noted that the galaxy has many pockets of high-speed ionized gas that might be ridden around the galaxy or out toward the rim, and that it may also be used for slowing from higher but still modest interstellar speeds by spiraling into a solar system.
See also Electric Solar Wind Sail, Solar Sail. Magnetoplasmadynamic Thruster.
The Magnetoplasmadynamic Thruster, or MPDT or MPD Arcjet, or Lorentz Force Accelerator, is another example of electric propulsion, but a potentially very high-speed one compared to your basic ion drive or resistor jet. The MPDT is fed on ionized gas, with everything from hydrogen to neon, argon, or xenon being good, but lithium having the best known performance to date. The acceleration chamber is acting on the principle of the Lorentz force or electromagnetic force, as opposed to electrostatic or magnetic forces alone, and this is what is accelerating our plasma, and as with similar designs, we have a lot of erosion of our cathodes. This, combined with it being a power hog, needing hundreds of kilowatts to run efficiently, often make it of low interest for satellites and small probes. That is no bar to uses for larger ships and manned interplanetary missions, however, and is a popular candidate for those options, where you would expect to have lots of power and a crew able to do some maintenance. In theory, a MPDT could achieve an exhaust velocity of over 100 kilometers per second, though just over half that is more common in tests, but that would be sufficient for interplanetary travel and at the lower edge of viable interstellar travel, as we discussed in our episode Colonizing the Galaxy. It also has a very high thrust compared to most other electric propulsion techniques, permitting not just a high final speed, but an acceleration rate to it that is not super slow.
See also Arcjet, Ion Drive, Resistojet, VASIMR. Matter beam.
Matter beaming is an example of how we can circumvent the rocket equation by accelerating matter at some stationary facility to push on a ship, much like a laser sail, but such matter beams in theory could also refuel a ship. A beam of oxygen could provide air to breathe and shove on a ship from behind, as a simple conceptual example. This is typically thought of as a stream of ionized atoms fired out of a long linear particle accelerator, and has the problem they would tend to shove off each other, being ionized and like particles of the same electric charge repelling each other, causing the beam to spread out too fast. Numerous workarounds have been proposed, though it should be noted this could also include actual cargo pods rather than microscopic particles, as a ship may catch such a pod in its own net, a long decelerator, or a pod might be designed to vaporize near a ship so that scattered atoms spread to push on the sail or pusher plate, and such a pod can have limited guidance and transmission packages on it. Regardless of focusing methods and their effectiveness, matter beams are far more useful than laser sails for pushing ships up to speed while they are moving up to or at interplanetary velocities. Matter beaming is a parallel concept to energy beaming, though there it is assumed we will be using photons and electromagnetic waves, and principally to transfer power, which we discuss more in the laser sails entry.
See also laser sail, magnetic solar wind sail. Medusa Drive.
The Medusa Drive is a variation of post-nuclear drives that replaces the pusher plate behind the ship with the equivalent of a parachute in front of the ship. A large sail assembly connected to the ship by a very long tether is shoved forward by detonating nuclear bombs inside the sail, and much like the normal Orion Drive's pusher plate, this shoves the sail forward, which then drags the ship along by the tether, rather than shoving the plate forward to push the ship from behind.
See also Nuclear Pulse Drive, Orion Drive. Microwave Electrothermal Thruster.
Whether generated by an internal power source or beamed in as microwave energy beam, it is possible to use microwaves inside a spaceship much as we use them in our kitchens, to heat matter up. The Microwave Electrothermal Thruster, or MET, does this, and much like the Arcjet Rocket, igniting a plasma in a propellant gas. Electrothermal thrusters all work on the concept of using electricity to heat the propellant, and as mentioned, this electricity might be supplied internally by reactor, RTG, or battery, or by solar panels or beamed in. As electrothermal propulsion goes, the MET is usually considered superior to the Resistojet due to its higher specific impulse, but inferior, or at best roughly equal, to the Arcjet. Electrothermal thrusters in general are popular mostly for their simplicity as an electric propulsion system, as they are generally neither efficient nor high thrust, even for electric propulsion. One advantage they do have is fuel, as a MET can run using water as its propellant, which is super abundant throughout the cosmos.
See also Arcjet Rocket, Laser Sail, Resistojets, Solar Moth. Negative mass propulsion.
Negative mass propulsion is a catch-all term for any drive that relies on the properties of negative mass, generally how it should warp space to expand around it, opposite of normal matter contracting space around it, or be pushed towards you if you shove on it. As no negative mass has ever been detected, any negative mass technology currently qualifies as Clarketech, and this includes most warp drive and wormhole proposals. There are multiple versions of how negative mass should operate, depending on if it is negative inertial mass or gravitational mass, active or passive, or some combination thereof. In the most commonly discussed version, it is generally assumed that positive mass will attract both positive and negative masses, and negative mass particles would repel both positive and negative masses. As a result, two positive mass particles pull toward each other, two negative mass particles repel each other, and a positive and negative mass particle will actually shove the positive mass away from the negative mass, while pulling the negative mass toward the positive mass, resulting in the positive mass particle being chased by the negative one. This is the basis of reactionless spaceship propulsion concepts like the Diametric Drive, and we discuss variations of negative matter in our episode Clarketech Anti-Gravity.
See also Alcubierre Warp Drive, Bias Drive, Clarketech, Diametric Drive, Pitch Drive, Warp Drive, Wormhole Drive. Neutrino Rocket.
Neutrinos are very low-mass, high-speed particles that normally do not interact with regular matter, being more likely than not to pass through an entire planet without being absorbed. If you could manipulate them, they would be very handy as a rocket propellant, as that would not superheat air or structures around them, or shake the ground, allowing for quieter propulsion. A neutrino rocket currently would qualify as Clarketech, as it would require technology that either allowed for the near-total reflection or absorption of neutrinos or their production in a directed fashion. Such technology or materials generally imply the ability to have far more efficient fusion reactors. While a rocket being made of neutrinos is useful for stealth purposes, as neutrinos are hard for us to detect, this probably only assists in stealth against lower-tech targets, as it may be assumed that anyone possessing this ability also has a very good neutrino detector too. It would remain a valuable propellant for its low heat transfer rates to objects around it. It potentially would represent a quiet aliens technology for the Fermi paradox as well, as the implied technologies of stealthy neutrino drives that emitted little heat or noise would also have advantages being used in other energy and industrial applications.
See also Clarketech Photon Rocket. Nova Drive.
Nova drives, along with their big brother, the supernova drive, are a method of moving dead stars such as white dwarfs by delivering a stream of hydrogen to them to cause a small nova. This is a parallel technology to the Orion Drive, which propels a ship with nuclear bombs, only vastly bigger. See our episode Fleet of Stars for more details.
See also Helios Drive, Pulsed Nuclear Drive, Orion Drive. Nuclear Electric Ion Drive.
A nuclear electric ion drive, also called a nuclear electric rocket or nuclear electric propulsion, refers to any type of drive where a nuclear reactor, fission or fusion, is being used to generate heat to convert into electricity, which in turn is used for electric propulsion, such as an ion drive, where charged particles are accelerated by electrodes or electromagnets to serve as a high-speed propellant. This would apply to a ship that was running a nuclear reactor as its main way to heat the ship, run the lights, life support, and other equipment, and use excess power to run the ion drive propelling the ship. As there was always some significant loss in converting energy at each step, as well as additional equipment to buy, carry, wear down, and maintain, many nuclear designs seek to circumvent the normal heat engine producing electricity for options like the nuclear light bulb, nuclear thermal propulsion, or nuclear pulse approaches.
See also Ion Drive, Fusion Torch Drive, Nuclear Light Bulb, Nuclear Pulse Drive, Nuclear Thermal Propulsion. Nuclear Light Bulb.
While a nuclear light bulb drive might seem like a photon rocket at first glance, and indeed could be modified to act as one, the purpose of a nuclear light bulb is to take a gas core fission reactor rocket, run at roughly 22,000 Kelvin, and give it a quartz wall, which is transparent to photon emissions at that temperature, which are mostly hard ultraviolet. Again, the light could be allowed to move out the back, making for a weak but reasonable photon rocket, since the power source is nuclear and energy dense. Instead though, we run it into a propellant that absorbs those ultraviolet photons, and which we would expect to provide an exhaust velocity possibly as high as 30,000 meters per second, far better than our best chemical fuels, and quite reasonable for interplanetary spacecraft. For details, see our episode The Nuclear Option.
See also Nuclear Electric Ion Drive, Nuclear Pulse Drive, Nuclear Thermal Propulsion, Photon Rocket. Nuclear Pulse Drive.
The nuclear pulse drive, also called external pulsed plasma propulsion, is best known for its Orion Drive variation, which uses nuclear bombs detonated behind the ship and pushing it to higher speed, relying on the vast amounts of energy proportional to mass that nuclear detonations have. These are not always large bombs or at a very high rate of explosion. Ideally, we would like very small nukes to detonate almost continuously to produce the equivalent of a nuclear rocket flame, but generally, bombs are both cheaper and more efficient the bigger you make them, and we must resort to ultra-rare artificial elements or antimatter catalyzed fusion to contemplate very small nuclear explosions more equivalent to a typical bomb or even less than a hand grenade. Your basic design calls for a large and sturdy plate behind the ship, called the pusher plate, which can absorb or reflect the photons released by the blast, and this shoves it forward where it slams into a layer of immense springs, which slowly push the plate back into place to await the next detonation while moving the ship forward at a more modest acceleration, translating the rapid shove of the plate into a protracted push on the ship. The Medusa variation uses a forward sail to absorb the blast, which is attached by a long and somewhat elastic tether to the ship. While the Orion Drive was the first major design of this type, we have other variations, such as Project Daedalus, which imagined detonating lithium deuteride pellets with a laser and a small deuterium and tritium trigger at its center, not unlike the laser fusion method used at the National Ignition Facility. This would release very modest fusion-powered explosions to run the ship. Were we ever able to produce a material able to reflect gamma rays, which would be invaluable for both fusion and many other high-energy applications, this would make a superior pusher plate option, reflecting rather than absorbing the gamma rays and achieving twice the momentum per detonation. Nuclear pulse drives are mostly unprototyped, minus some early work in the 50s and 60s and later modeling, but are considered buildable and do have the ability to reach speeds which would allow interstellar travel. See our episodes The Nuclear Option and Revitalizing Project Orion, a new dawn for nuclear spaceship propulsion for more discussion of this technology and its variations.
See also Antimatter Catalyzed Fusion, Medusa Drive, Nuclear Electric Ion Drive, Nuclear Pulse Drive, Nuclear Thermal Propulsion, Orion Drive. Nuclear Thermal Propulsion.
In a nuclear thermal propulsion system, we have a reactor which is being cooled much like a normal fission reactor, but that heat is used to superheat a propellant. While the individual engineering varies and is complex, the basic concept is as simple as that. Cool your nuclear reactor with your future propellant, and try to get that propellant as hot as you can without melting things, which is more difficult if you're attempting closed loops that make sure your actual propellant is not getting radioactive. While it is possible to run an open-cycle reactor that would blow radioactive propellant out the back, and rather cheaply and efficiently, this is not considered a viable method of spaceship propulsion on or near Earth, or honestly any place people will be hanging out at. Either closed or open-cycle NTPs make interplanetary missions much easier, and of course space is empty of basically everything but radiation already, so other than shielding the crew, we mostly need to ensure safety when approaching or leaving inhabited places. While they are usually advertised as never being used to get off Earth, from a realistic perspective, this is reasonably safe with a closed-loop NTP, not particularly more or less dangerous than a normal rocket to those who might be near it or get hit by its debris on a failed launch, and thus may one day become common in launch vehicles. In the meantime, though, it is contemplated as a second-stage system used to travel from some space station in high orbit of Earth to other worlds, with conventional rockets or alternatives like space elevators being used to get to that station.
See also Nuclear Electric Ion Drive, Nuclear Light Bulb, Nuclear Pulse Drive. Orion Drive.
The Orion Drive is the best known example of nuclear pulse drives, using nuclear explosions behind the ship to propel it to very high speeds, sufficient for interstellar travel. See our episode Revitalizing Project Orion, a new dawn for nuclear spaceship propulsion for details.
See also Medusa Drive, Nuclear Pulse Drive. Oxidizer.
While every rocket needs fuel to burn, it also needs an oxidizer, as no fire can go without oxygen to breathe, and indeed molecular oxygen is the most common oxidizer. In most cases, a rocket's propellant will be a byproduct of the combustion of the fuel with the oxidizer, carbon dioxide and water being plentiful in most rocket exhaust, as well as plane and car exhaust.
See also Chemical Rocket, Propellant, Rocket Equation. Photon Rocket.
The key to a good rocket is a high exhaust velocity, fast-moving particles coming out the back of your ship, and the faster the better. And with the possible exception of exotic hypothetical particles like tachyons, nothing moves faster than photons, the particles of light that travel at the speed of light, and of gravity. This is where the photon rocket comes in, sometimes called a flashlight drive. This is a device that shoots photons out as its rocket plume, possibly light, possibly even a laser beam, maybe different frequencies like microwave or gamma rays or even radio. Such a ship, if it could contain a large portion of its mass as photons, waiting to be propellant, or something it turned into photons, like antimatter or Hawking radiation off a black hole, would allow a ship to travel at near light speeds. Now, the problem with a flashlight is that your typical modern battery contains less than 1,000,000 joules per kilogram of battery, about a megajoule, just a percent or two of what an equal mass of gasoline or rocket fuel has. And while an actual kilogram of photons, or its mass energy equivalent, would be an amazingly powerful rocket fuel, that wouldn't be a megajoule, but rather 90 billion megajoules. That drained battery only lost a few nanograms of mass, not a kilogram. We might imagine some box made of perfect mirrors that light bounced around inside, frozen light essentially, or options for things that convert some or all of their mass into photons, nuclear reactions, antimatter, evaporating black holes, and so on. If you have these, photon rockets are a good approach to achieving very high speeds. For lower speeds though, you'll get more thrust from the same energy by applying it to a propellant. A particle of hydrogen that soaked up a 1 MeV gamma ray and flew out of your ship is going to have more momentum exchange, and thus yield more thrust than the gamma ray alone did, but it also has 938 times more mass energy than that photon carried, and is now only moving away at 4,400 kilometers per second, which is dozens of times faster than any spacecraft we've ever made, but still only about 1.4% of light speed. With that in mind, unless you have a matter-to-energy converter, like the Torch ship has, ships moving in interplanetary space, even if possessing a photon rocket, will still opt to use that energy to superheat propellant, as they should have little difficulty tanking up on hydrogen or some other plentiful propellant while in system. This is essentially the notion of a nuclear light bulb drive.
See also laser sail, matter beaming, neutrino rocket, nuclear light bulb, propellant, rocket equation, torch drive or torch ship. Pitch drive.
The pitch drive is a hypothetical Clarketech reactionless drive where a field or force can be used to create an effective pressure difference on the ship to push it along. Diametric drives are a subcategory of pitch drives where there is a source for the force, like a ball of negative mass. Pitch drives in a wider sense do not require a source and would include technologies that simply cause some force or pressure difference to appear on your ship. This is a general concept rather than a hypothetical engine, so no specific cases are involved, and it would qualify as Clarketech. This technology is also akin to a gravitational dipole drive when gravity is the force or field being used for propulsion, and negative mass is available.
See also bias drive, Clarketech, diametric drive, gravitational dipole drive, reactionless drive. Propellant.
Propellant is the term for anything leaving a spaceship with the intent of adding to its momentum, and typically this is the byproduct of combustion of the rocket's fuel with an oxidizer, though a propellant can also be ions slung out of the ship by electric propulsion or photons produced by an antimatter reaction. All things being equal, your optimal propellant is fast-moving, with a high exhaust velocity and specific impulse, and this can include light speed or near-light speed particles like photons, gravitons, neutrinos, or various other lesser-known or hypothetical particles.
See also antimatter rocket, exhaust velocity, fuel, oxidizer, neutrino rocket, photon rocket, rocket equation, specific impulse. Pulsed inductive thruster.
A pulsed inductive thruster, also known as a PIT or PIT, is another example of an ion drive, but one using both magnetic and electric fields. It is popular for its lack of electrodes, which tend to be a weak spot of other ion thruster designs as they are eroded by use. PIT have a nozzle that sprays a small puff of gas toward a flat electromagnetic coil, which a bank of capacitors will then pulse up to many thousands of volts for just a few microseconds. This causes the gas to ionize and move in a circle opposite the original direction, making it a plasma flowing perpendicularly to its magnetic field, which is ideal for the Lorentz force to grab and hurl out the back of the spaceship at tens of kilometers per second. PIT is also scalable to higher powers, with a megawatt system able to pulse it a couple hundred times per second, making for decent thrust. And it's relatively omnivorous for propellant, able to use everything from water or carbon dioxide to ammonia or hydrazine to argon or xenon, which makes it attractive for use on Mars missions, where it may be able to refuel while orbiting from scooping Mars's carbon dioxide-rich atmosphere.
See also ion drive, Magnetoplasmadynamic Thruster, quantum vacuum thruster.
Also called a Q-thruster, the quantum vacuum thruster is a hypothetical space drive making use of the Casimir effect and quantum mechanics. It is the current belief of physics that at the quantum scale, we have a constant ebb and flow of electromagnetic waves and virtual particles pop in and out of existence. We discussed this more in our episode Antimatter Factories, where we explain how virtual particles and C and valence quark interactions are thought to take place. In summary though, we generally think of what we call the vacuum of space, sucked of all normal matter and walled off from outside radiation, to still not quite be a vacuum. Rather, it is a false vacuum that still has all these electromagnetic waves and virtual particles popping in and out of existence on the hazy edge of reality. They exist for an instant, but there's always a ton of them, amounting to a constant supply and density. If you ever heard of the VASIMR effect, this is where we put two very flat and uncharged conductive plates just a few nanometers from each other, barely enough room for a few atoms. This generates a very small repulsive or attractive force or pressure on the plates depending on the arrangement. While you can get a similar effect inside any medium that's oscillating like water, empty space and vacuum isn't supposed to have any of that, no medium to oscillate. This was quite mysterious and is where we get concepts like vacuum energy and false vacuum from, experimentally anyway. One way of thinking of this is that no virtual particle can appear between those two plates whose wavelength is bigger than the plates, which means if you get them close enough, no virtual particles could appear, making for an even more vacuumy vacuum. This means the plates are experiencing a net force from outside, where the vacuum is just normal and thus greater than inside, and we can use that to create power. Key bit there, if the quantum was getting confusing, we can generate power, or thus photons or other particles, out of nothing at all, and thus don't have to carry them with us, particles we can use as a propellant. Meaning we now have a photon rocket, or neutrino rocket, or a plasma of whatever particles or waves are emerging from our plates, which are going to keep pumping them out. It is debatable if this would qualify as a reactionless drive, since it is generating reaction mass, since this would seem to blatantly violate conservation of energy and momentum, and make for a very simple perpetual motion machine. It is generally assumed to be Clarketech. It is also very similar conceptually to the EM drive, which is better known and more recent, though this technology continues to be discussed and seriously. For those wanting a deeper dive, Centauri Dreams has had several articles discussing it and variations over the years.
Quasar Drive.
The Quasar Drive is a scaled-up black hole drive capable of moving planets or entire galaxies, and is the ultimate engine for moving large objects, being both faster than the Shkadov Thruster to accelerate stellar objects, and more efficient, allowing faster final speeds. The Quasar Drive takes a charged black hole, artificial or natural, builds a structure around it to attach to it magnetically, and injects matter into it to produce power production, as is typical for large-scale black hole power generators. This is then used to run a drive able to achieve a decent fraction of light speed. The name Quasar Drive is derived from quasars, the super bright objects which are typically thousands of times brighter than entire galaxies, as a result of matter falling into black holes in the center of many galaxies. Used carefully, a quasar drive on a supermassive black hole in the center of a galaxy can move that galaxy, especially if used in tandem with many other drives throughout that galaxy, gravitationally dragging that galaxy along, which may permit a sufficiently advanced civilization to counteract Hubble expansion in a large region of space, such as a galactic supercluster, and potentially several billion light-years around, though much of the galaxy's mass must be used to power the trip the further out you go, as Hubble expansion rises by roughly 7% of light speed for every billion light-years of distance. Planet ships using quasar drives represent a plausible approach to intergalactic colonization of even galaxies more than a billion light-years away. See our episodes Fleet of Stars and Intergalactic Voyages for more discussion of this.
See also Shkadov Thruster. Reactionless Drives.
Newton's third law says that for every action there is an equal and opposite reaction, and this is critical to spaceflight, but also has a strong limit on it. All modern spacecraft work by using a propellant to provide reaction mass, matter being expelled at speed out the back of a spacecraft to push the ship the other way. Those particles flying out the back have a certain mass and velocity, and mass times velocity is momentum, a quantity which must always be conserved, so the ship gains that same added momentum. This means immense amounts of propellant must be expelled, and that every new bit of propellant you carry takes more propellant to push, which we call the tyranny of the rocket equation. Outside of a vacuum environment like space, we can cheat around this. When walking, we can push off the ground, which provides our reaction mass, the Earth being shoved ever so infinitesimally the other way. An aircraft can do the same, burning fuel but using the air to suck in and push out the back. Such options are not available in a vacuum, and even a spaceship having photons or matter bounced out from the outside while circumventing the rocket equation still represent reaction mass, much as us stepping on Earth and shoving off it, or an air-breathing engine on an airplane or jet. Thus, a reactionless drive is usually considered Clarketech, but it is contemplated with spaceship drives such as the Alcubierre Warp Drive, Diametric Drive, EM Drive, Field Propulsion, and Gravitational Dipole-driven ships.
See also Alcubierre Warp Drive, Diametric Drive, EM Drive, Field Propulsion, Gravitational Dipole Drive, Propellant, Rocket Equation. Resistojet.
Resistojet rockets are an example of electric propulsion, using a power supply to create electricity that we then run through resistors to produce a hot incandescent filament, same as a classic incandescent light bulb, which in turn heats up an inert material that becomes the rocket propellant. Resistojets are commonly used in satellites and have been for decades, as they provide the benefit of decent specific impulse like hydrazine does, but the safety of an inert propellant like cold gas thrusters have. This makes it good for minor course corrections and long-term use over many years. It can also be used in conjunction with a power supply like an RTG or solar panel. It should be noted that it is not very efficient compared to its cousins, the Arcjet and the Microwave Electrothermal Thruster.
See also Arcjet, Microwave Electrothermal Thruster. Reusable Rocket.
While much discussion of rocketry has to do with better fuels with higher exhaust velocities or higher tech propulsion, most of the cost of modern rockets and space launches, currently and in the past, was not the fuel, but the rocket body itself, which must be precision-tailored and incredibly tough to handle the insane forces, pressures, vibrations, and heat involved in launch. As a result, the easiest path to cheaper space travel has been seen as either recovering and reusing those rockets or repurposing the booster shells left over in orbit as space station components. These days, we can not only use parachutes to slow a booster falling back to the ground, but reserve some fuel to gently re-land it, as SpaceX has often demonstrated. However, reuse is still harder than it sounds, since even a rocket body that isn't slamming into the ground at high speed or falling into corrosive seawater has still been through a burn, which tends to cause cracks and warping and requires careful inspection and reuse. Super materials that were more resistant to this wear and tear would vastly cheapen rocket launches, allowing quick and easy reuse, such as we see with automobiles and planes. See our episode Reusable Rockets for more discussion of this topic.
See also Exhaust Velocity, Propellant, Rocket Equation. Rocket Equation.
The rocket equation governs how fast a ship can go based on the speed its propellant moves out of the ship, its exhaust velocity, and the ratio of its initial mass when full of a rocket fuel and oxidizer to its final mass when that fuel is expended and only the ship and the payload it is carrying remain. For a rocket to achieve the same speed as its exhaust velocity, but in the opposite direction, it must have nearly double the amount of fuel as rocket and payload combined. Alternatively, to achieve half that speed, it would only need about half as much fuel and oxidizer as rocket and payload. This means a 10-ton pod, being launched with a 10,000 mph exhaust velocity propellant, can achieve 5,000 miles per hour with roughly 6.5 tons of fuel, but would need almost 17 tons of fuel to get to 10,000 miles per hour. To get to double the exhaust velocity, 20,000 miles per hour, fully 64 tons of fuel, and to go 3 times the exhaust velocity, 201 tons of fuel. This sharply rising curve is why we often hear the expression, in regard to space travel, of the tyranny of the rocket equation. Most chemical rocket fuels have exhaust velocities of thousands of meters per second, or as high as roughly 10,000 miles per hour, but to reach low Earth orbit, and ignoring losses to air friction during your climb, you must reach almost 8,000 meters per second, or 17,000 miles per hour. To go to other planets, even more, and interstellar travel speeds must be tens to hundreds of times higher to be practical. While we do have higher exhaust velocity options, in general we must often sacrifice rate of thrust to achieve a more efficient higher final speed from a higher exhaust velocity. Virtually all discussion of advanced propulsion is about trying to find either higher exhaust velocity propellants or to circumvent the rocket equation with options like reactionless drives or laser sails.
See also Exhaust Velocity, Fuel, Laser sails, oxidizer, propellant, reactionless drive, specific impulse, thrust. Shkadov Thruster.
A Shkadov Thruster is a type of stellar engine designed for using a star's own power to move it, by surrounding the star in orbital mirrors or statites, which reflect light in one direction. With this method, stars can be slowly accelerated up to a small fraction of light speed. Bigger stars accelerate faster as they have a higher brightness to mass ratio, whereas smaller stars can attain higher ultimate speeds as they burn a large percentage of their fuel. All versions are slow though, and because of the acceleration time, it is a relatively minor difference in effort to move them across a galaxy or even between galaxies compared to simply moving them a few systems over. See our episode Shkadov Thrusters and Fleet of Stars for more discussion.
See also Caplan Thruster, Helios Drive, Nova Drive, Quasar Drive. Solar Moth.
A solar moth is a type of solar thermal rocket that uses a parabolic mirror, or wing-like pairs of them, to focus light from a nearby star on a tank of future propellant, the tank likely being half silver to allow light in and keep it bouncing around to heat the gas inside the tank. This superheated gas then makes for an excellent propellant. We may also use this in conjunction with laser beaming or microwaves or any other type of energy beaming to achieve a higher thrust. This approach allows for a higher thrust than a simple solar sail or laser sail, though that thrust comes to an end when the propellant runs out, and then it will simply be a solar sail, the one moving faster sooner and bearing less cargo and payload. It may be very useful for forward deploying laser beaming equipment to new star systems. Like a laser sail, it can be used in conjunction with a matter beam to replenish propellant too. A solar moth is a very simple design with few failure modes, and a solar moth might use very nearly anything that can be vaporized as a propellant, including common elements in deep space like hydrogen, water, methane, or ammonia, making them a potentially good engine for probes and long-term monitors in the asteroid belt or Kuiper belt. Scaled up, a solar moth is a good way to move a comet, simply using it as propellant, as energy beamed to it from in-system will create far less outward thrust than the energy received being used to vaporize ice and shove inward toward the solar system's inner regions.
See also laser sail, matter beam, solar sail. Solar sail.
Solar sails operate on the principle that photons of light carry momentum which may be absorbed by opaque objects, transferring that momentum, or reflected by reflective objects or mirrors, which can double the imparted momentum, sending the photon back with the same but opposite momentum, or deflecting at an angle to send both sail and deflected photon off in different directions. This allows a sail to quarter sunlight. The weakness of a solar sail is the need for a very large thin sail to reflect enough sunlight to shove a relatively tiny spaceship. That sail, even made from super thin materials, remains a target of micrometeors, can be eroded by space dust and radiation, and if big enough, is a navigational hazard. Sunlight also drops off inverse square the distance, meaning a solar sail twice as far from the sun is getting only a quarter of the push. And so a sail at Mercury pushed out to Pluto is receiving many thousands of times less push at the end than at the beginning. With this in mind, we have options like laser sails, which are simply solar sails which a laser is focused upon, and electric and magnetic sails, which can use ionized solar wind particles or matter beams to fill and push their sails. Solar sails can also be used to maintain stationary or atypical orbits, as with statites.
See also antimatter ablated light sail, electric solar wind sail, laser sails, magnetic solar wind sail, matter beaming, statite. Specific impulse.
Specific impulse is the twin to exhaust velocity, and both are used to measure how effective a given rocket fuel, propellant, or spaceship drive are, while exhaust velocities measure how fast particles of exhaust come out of a rocket nozzle or other spaceship drive. Specific impulse, abbreviated as ISP, is a measure of how efficiently the engine creates thrust. It is measured in how long the engine can produce that thrust, and the default measurement is based on how many seconds an engine could operate at 1 g of thrust, the amount needed to hover a rocket right over the ground on Earth, neither rising nor falling. Most modern rocket fuels will be on order of a few hundred seconds, and it should be noted that some lower specific impulse fuels will be more useful in certain situations, or that specific impulse can be altered based on if you're in the atmosphere or not. Such being the case, we will often use lower specific impulse boosters to get off the ground. A propellant's exhaust velocity divided by the gravitic acceleration of Earth, 32 feet or 9.8 meters per second, will give the approximate specific impulse of a propellant, and vice versa, multiplying specific impulse by gravitic acceleration will yield exhaust velocity.
See also exhaust velocity, fuel, oxidizer, propellant, reactionless drive, thrust. Statite.
The statite varies from most propulsion systems in that its aim is to keep an object stationary rather than moving it. Statites are the brainchild of Robert Forward, who suggested the name in 1993 as a mix of static and satellite. A statite is able to hang directly above a star rather than circling it in a typical orbit. These make use of the radiant pressure of sunlight to allow very thin objects perpendicular to the sun to hover in place by balancing the amount of force the sunlight exerts against the gravity of the sun. A statite must be carefully balanced in terms of its cross-section density so that it doesn't float further away or fall closer, and thus would likely include the ability to adjust its cross-section and tilt to allow it to engage in station keeping or even moving as a solo sail. The critical factor of statite function is surface or cross-section density, how thick the statite is, and this will generally be on the order of tin foil or thinner. As the strength of light and gravity both fall off inverse the square of distance from the sun, a statite of a given surface density functions regardless of its distance from its star. However, it would not function around any star with a different brightness to mass ratio. Statites are far easier to make function around more massive stars, which are far brighter, than they are around less massive dwarf stars, as stars can vary by a factor of around 100 in mass, but more than 1 billion in brightness for that range. Variations of these can also use magnetics to deflect solar wind ions as an alternative to sunlight or in combination with them. So too, the use of focused sunlight from solar mirrors or beams can be used to allow heavier statites. The laggite version of this, being a combination of lagging and satellite, is where we can mix normal orbits and propulsion with a statite to produce an object that orbits at an unnatural speed, such as low Earth orbital object that orbited Earth 2 times per day rather than every 2 hours, or a near-Mercury orbit power array that remained in conjunction with Earth as it orbited the Sun every 365 days to beam power home.
See also Shkadov Thruster. Teleportation.
While teleportation is most familiar as a short-range point-to-point transfer, such as the transporters in Star Trek, this general category of space travel can refer to any drive that circumvents travel between 2 places to deposit you immediately there, and thus differs from hyperspace jump ships, which typically involve moving to a parallel and congruent space or reality where either the space is smaller or the speed of light is higher. Examples of this vary wildly and might include the Holtzman drive utilized by the Spacing Guild in Frank Herbert's Dune series, or the intended use of the drive in the movie Event Horizon for the ship of the same name, which is described as instantly moving between 2 points, but instead turns out to be a type of hyperdrive, much to the crew's dismay. Teleportation, especially for FTL purposes, is usually considered Clarketech, but for possible teleportation methods under known science, see our episode Teleportation.
See also Clarketech, FTL Drive, Hyperdrive. Thrust.
Thrust is what makes ships move. The more they experience, the faster they accelerate, and the longer they accelerate, the faster they go. But the bigger they are, the more thrust they need to push themselves. Most often in spaceships, this is produced by a rocket flame expelling superheated gas out of the ship, pushing on it in the other direction, and providing a high thrust. High thrust is good, as we cannot get off a planet without a high thrust, and the faster we can get up to speed, the shorter our journey time. However, in practice, almost all high-thrust technologies are low efficiency, allowing a quick acceleration to a modest speed, and lower thrust engines like an ion drive allow for very long accelerations to a higher final speed. The holy grail of spacecraft propulsion is a high-thrust, high-efficiency fuel, such as a torch drive or antimatter rocket.
See also Antimatter Rocket, Fuel, Fusion Torch Drive, Oxidizer, Propellant, Rocket Equation, Torch Drive. Torch Drive or Torch Ship.
While the term torch drive is often used to discuss fusion reactions, which generally convert no more than 1% of the fuel's mass to energy, its original usage was on a torch ship in Robert Heinlein's 1953 short story, Skylift, where it was able to convert 100% of matter to energy, which generally means it can achieve an order of magnitude higher velocity than a fusion drive, and parallels the performance of antimatter drives. Converting matter directly into energy is preferable to antimatter, as it implies the ability to load any matter into your spaceship, harvested from any source, as opposed to needing complex and dangerous antimatter production and storage. Some consider a ship a torch ship if its exhaust velocity multiplied by its thrust amounts to a very large figure, for example a high-speed and high-thrust ship like those in The Expanse, or perhaps a low acceleration but very large ship that puts out hundreds of terawatts of power even as it's pushing a few millig's.
See also Antimatter Drive, Fusion Torch Drive. VASIMR.
The Variable Specific Impulse Magnetoplasma Rocket, known by the acronym VASIMR, is a spaceship propulsion technique utilizing an electrothermal thruster, using electricity generated by a reactor, battery, or solar panel to generate radio waves, which then ionize a neutral and inert propellant, generally xenon or argon, noble gases with no net electric charge. Once ionized by the radio waves, they lose an electron and gain an electric charge, and are injected into a hollow cylinder full of electromagnets which shove on the now ionized particle, much like a particle accelerator, and it propels out the back of the ship at the equivalent temperature of 1,000,000 degrees, rather than the low thousands of most chemical rocket fuel exhausts. VASIMR and parallel engine concepts allow a ship with a good power supply, such as a nuclear fission or fusion reactor, or external power such as solar or energy beams, to achieve very high speeds on a very small amount of fuel.
See also Hall Effect Thruster, Ion Drive. Warp Drive.
While the Alcubierre Warp Drive and Star Trek Warp Drive are the best known examples of warp drives, this category predates both concepts and relies on the notion that a spaceship has to travel through space, and thus warping space or space-time becomes an attractive option. If we can warp space to make two pieces of it meet, like folding a paper map in half to make London touch Los Angeles, or contract it to just shorten the path, we can make my trip faster or easier. Since Einstein's relativity tells us space-time can be warped, and this has been experimentally confirmed many times, much speculation of using this for moving ships has been contemplated. Additionally, warping space-time circumvents normal relativistic restrictions on traveling faster than light speed, and potentially offers travel with little fuel or energy used. It should be noted that problems will still tend to arise using space warping for FTL purposes that likely make this usage impossible, but such space warping can still be practical for sublight travel and indeed could be argued to be at work in a gravity assist maneuver, since large bodies like planets, stars, and black holes all warp space-time. However, most warp concepts require not just contracting space, which normal mass and gravity do, but also expanding space, which requires the use of negative mass or energy, and negative mass has not yet been documented to exist, nor negative energy outside of the debatable case of the Casimir effect and vacuum energy.
See also Alcubierre Warp Drive, Black Hole Ships, Clarketech, Faster Than Light FTL Drives, Negative Matter Propulsion, Quantum Vacuum Thruster, Wormhole Drive. Wormhole Drive.
A wormhole drive is an example of a type of Clarketech utilizing a wormhole not to travel along, but to bring fuel in from. If wormholes are possible to create, it is likely that you would have to create the entrance and exits at the same place, and then move them apart, or that the exit would appear at a random place, possibly deep in a gravity well or in another universe. They may also be one-way or destructive on passage, scrambling data and objects that pass through, irrecoverably. Should any of these be true, another way to use a wormhole for travel would be to place one end in close orbit of a star or even inside it, and the other end on the back of your ship, allowing huge amounts of thrust to be produced without needing to carry it along, thus circumventing the rocket equation. Parallel methods for Stargate-style portals would also permit matter or laser beams to be sent to ships or the transfer of cargo or personnel.
See also Clarketech, Matter Beam, Photon Rocket.
We looked at a lot of spaceship engines today, from the classics to distant far future, some of which might let us travel to other worlds. But for now, we have rockets, and a very real concern is how much we could scale up using them before it becomes an environmental problem. It is a sad reality that a lot of our technology, especially in transport, has various negative or disruptive impacts on the environment, whether it's deforestation or carbon emissions or air and water quality. There is often a lot of disagreement about what to do about these problems, But if you ever want to find out how you can make a difference, you can visit REN's website and answer a few simple questions to calculate your approximate carbon footprint and see a list of options like planting trees, mineral weathering, or rainforest protection to offset your total. REN is a climate-centric, public-benefit corporation that lets people sign up for a monthly subscription equal to their carbon footprint, which for most folks is less than $20 a month. Carbon offsets are a controversial space, with a lot of projects failing to live up to their potential. REN deep dives a project's finances, gets third-party experts to evaluate them, and does its due diligence by asking potential project partners over 80 questions to make sure they have a financially, logistically, and scientifically sound project. Like their tree planting project in East Africa, which helps subsistence farmers improve their land while planting trees, but also make sure to track real progress and make sure the trees are healthy and not just getting cut down again in 10 years. REN focuses on data-driven, transparent, and accountable projects. And if you sign up, you receive monthly updates from the projects you support. You get to see what your money is spent on, with photos and details on every tree planted, every acre reforested, every ton of carbon offset. And the first 100 people who sign up using the link in the episode's description will get their first month of subscription covered by REN for free. As a brief aside before we close out, as a lot of you probably know already, I was recently elected the president of the National Space Society, and it is a great honor to be heading up a group that has been working to help raise awareness and encourage research in so many of the topics we looked at today and in general on the show. And something of a happy coincidence, the NSS hosts a space forum every other Thursday evening, though not this week or next, and since I plan to get more actively involved in those, I am curious what topics or people folks would like to see over in those, so leave a note in the comments if you've got any suggestions. So that will wrap us up for today's very long episode and March, but we will be back next Thursday to start April up with another of our favorite topics, the Fermi Paradox, and a look at the concept of galactic habitable zones. After that, we'll head on back to modern Earth for a discussion of nuclear energy and small modular reactors, and an update on the state of that industry. Then it'll be time for our monthly Sci-Fi Sunday episode to contemplate superweapons, from the kind that blow up planets all the way to things that could rip holes in reality or kill universes. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also help support the show on Patreon, and if you want to donate and help in other ways, you can see those options by visiting our website, isaacarthur.net. You can also catch all of SFIA's episodes early and ad-free on our streaming service, Nebula, at go.nebula.tv/IsaacArthur. As always, thanks for watching, and have a great week.